recording up. Hopefully I don't fill up my hard drive. You guys all used Simulink before at all? Hopefully you've had some experience with Simulink. We might fire it up to do some investigations with Simulink. So for anyone wondering what's going to be covered and what sort of the background knowledge needed is, there's quite little assumed knowledge, not too much. Probably if you've done signals and systems is a good spot. So we talk briefly about Laplace transforms. So having some experience with what those are is handy. The ideas of systems and signals, inputs and outputs. If you've had any hardware experience, that's a bonus, but not 100% necessary. I think, you know, if you're undergraduate and done something like signals and systems or not quite, you'll be okay. Certainly if you're postgraduate, you should be okay too. If you're taking control systems at the moment, you'll certainly be okay. But yeah, it is an introductory course, so let me know how it feels for you guys. I'm not sure exactly what the best level to teach this to is. So yeah, if you need me to get more in depth or clarify anything, just let me know. Okay, I think we might make an official start. So my name's John. I'm with MUEC this semester, and I'll be running the control systems workshop today. We'll be talking about the different types of control and doing a little hardware demo as well. So we've got 2 hours pinned. The first hour or so will be mostly talking about theory and results, and then we'll have a little bit of a break at about an hour, and then after the break in the last hour we'll hopefully be moving on to hardware. So let's do it. And Knuckles says hi. Hello. Right, go away. So, yeah, as I said, we're mostly going to be taking a practical approach and learn the fundamentals of control systems. Particularly, I want to get you used to identifying control systems and where they are and how to see them, how to describe them, both intuitively and mathematically. So using mathematical rigor or some sort of mathematical rigor. The important terminology that's used, some canonical control schemes. So these are controller schemes that you can apply to a lot of different problems. So once you learn these, you're sort of pretty well set to tackle a lot of control problems. And then at the end, we're going to talk about implementing a control scheme on an Arduino microcontroller. And I'll talk a lot more about that later. So in broad terms, the control system, you use it to drive a physical system to some sort of desired state. And the control system manages how the system moves between those states and recovers from disturbances of the state. So familiar systems that you might be familiar and know that they use control or think that they might use some sort of control system. A toilet, there's some sort of control of water level in there. Air conditioning heaters, so controlling the temperature. Cruise control controls the velocity of your car. Servo motors, if you've ever used a little servo motor before, they actually implement a control scheme to control the angle of the servo, so there's a feedback loop in there. Locomotion, so we control the motor speed. Drones and quadcopters have plenty of different control happening on there, so attitude, elevation, everything like that, heaps of stuff. So we need to understand the language of control. That's what, you know, I'd love to jump straight into the actual doing, but there's a lot of terminology there that you need to be familiar with, so things make sense. So we do have to cover a little bit of background. As I said, if you've done signals and systems or the Simulink workshop that I ran earlier in the semester, you're in a pretty good spot. So if you haven't done signals and systems, or you need a bit of a refresher, here it is. System converts one or more input signals to an output signal. We describe systems with a block diagram, and a block maps an input to an output. Sometimes that's a simple mapping, sometimes it's more complicated. And blocks are joined with lines which represent the signal at that point. I'm going to speed up a little maybe. To design effective control systems, you'll find that most of the time we need to have some sort of understanding of what the actual system is doing, so what the dynamics of the system are. You'll see with the hardware example, sometimes it's not that important. We can actually just jump in a little bit and start designing the control system. It's a good idea to know what the actual system is doing, but you can sort of get away with just a sort of basic knowledge of what's going on. So to understand the system dynamics, we need to know the equations of motion that govern the system. So if you're using mechanical systems, it'll probably be Newton's laws, so F equals ma, and Maxwell's equations, or higher level versions of them, like Kirchhoff's laws and Ohm's law, for electrical systems. And sometimes they can combine the two, like with electromechanical actuators like motors or loudspeakers or something like that. So we certainly need to know about those equations of motion. As an example, you might derive the equations of motion, the system dynamics, for a DC motor. So a voltage source is connected to a DC motor. How do we describe the dynamics of this system? This is a basic model of a motor. There's an internal resistance, there's an internal inductance, and there's some sort of back EMF generated when the motor turns. Oops, wrong way. So how would we do that? First of all, we'd apply Kirchhoff's voltage law around the loop. Just all the voltages add up. And we need to implement some knowledge of what that back EMF is doing, which is this relation here. Constant times the rotational speed, so the rate of change of the angular position, or the angular speed of the motor shaft. We use that in the equation. We need to know how to link the motor current to the motor torque, which is by this relation. And then we can link that to the mechanical torque and the angular acceleration of the motor using this relation. So this is the rotational version of Newton's second law, basically. J, the moment of inertia multiplied by the angular acceleration, is equal to the sum of all the torques. And we found above that the torque is equal to this term here. And then we combine all of those together and we get this big, somewhat nasty, perhaps, differential equation. And it describes the system dynamics, basically, for that motor. And it maps the input voltage, V, to the output, which is the motor position or speed. And just a note there that usually this term, we can neglect that, that third order term. So if you're seeing this differential equation somewhere else with without this third order term, that's why, because we can usually neglect that. So this is just an example. DC motors are super common. But this introduces some important terminology for us. The system which maps the input to the output is known as the plant, and that's often denoted by the symbol of G. So a plant, when we refer to this generic thing of the plant, that's basically the thing that does the things that we want. We give it some sort of input signal, it does its system thing, and then it spits out some sort of output at the other side. So the motor, the input was the voltage, and the output was the rotational speed of the motor. And then once we've got this the plant differential equation, we can use our typical techniques for analyzing those equations. So Laplace transforms, super common for differential equations and working with control systems. And we work in the frequency domain. And we'll talk about that a little bit more. First, I want to talk about the idea of state variables. So state variables, they're the variables that describe the state of the system that we're working with. For the motor, there was the voltage, the angle and its derivatives, and also I, the current and its derivatives as well. And we saw with that motor, we were able to reduce the system and sort of factor out the current term, the I, and just get it down to working with the voltage and the angle. So we can sometimes reduce that out. Sometimes we can't actually do that, and we're just left with a system of coupled equations, which a little bit beyond the scope of this. But yeah, sometimes you're left with a system of coupled equations for the control system or the plant system. Sorry. So here's our plant block, and typically, by conventional, we denote the input to the plant block using the letter U. So the input is U, and the output is Y. That's just convention there. So sometimes U is referred to as the control signal or the control input, and yeah, Y will be the output there. You don't have to use them, but in general convention, that's what's used. Sometimes it makes more sense to refer to what this variable actually might be. So if it's a voltage, you might use V, and if the output is position, you might use X or D or something like that. But there is a sort of convention that we try and work to. How am I doing so far? Anyone completely lost? Anyone wishing I would speed up? Excellente. Feel free to yell out if you've got any questions. Happy for you to jump on the mic, make comments. Think of it like we're all in a room. It's a bit hard to avoid the feeling of like I'm giving a lecture to you guys. I don't want that to be the case, but unfortunately we're sort of stuck with this remote delivery style. So lecture format is sort of how it ends up anyway. So all right, equilibria. Probably pretty familiar. I think these images sum up equilibrium quite nicely, and you can sort of look at them and get an idea of exactly what they mean. So we have stable equilibrium points, marginally stable and unstable equilibrium points, and we can find them mathematically by just setting all derivatives of state variables to 0. So we don't need to, nothing's changing with time. So equilibrium makes sense, right? Typically when we're designing a control system, we want to aim for stable equilibria. That's what we want. And avoiding unstable equilibria. Because any small deviation from that equilibrium will make our output diverge or just shoot off. Our ball will roll off the hill. Sometimes with a control system, well, most of the time if we do have an unstable equilibrium, it's the job of the control system to stabilize that equilibrium point. So you can think of like an inverted pendulum. A pendulum sitting up on its end is inherently unstable. Any small movement away from that equilibrium, if you imagine you can sit a pendulum directly up perfectly to the atom, it's never going to move because the forces are balanced. But as soon as any tiny little deviation comes along, the forces are now unbalanced and it just falls away. And so that's an unstable equilibrium. But we can use a control system to stabilize that unstable equilibrium. And there's a lot of analysis that goes into what your plant is doing and how our control system should stabilize that equilibrium. And the idea of linearization is quite powerful. I'm not going to spend too much time on that one at the moment, but yeah, certainly a system can be non-linear sometimes, and yeah, there are a whole deep field of studying non-linear control and things like that. So it's quite a hard topic. There is techniques to linearize non-linear equations. We won't go through it now, but yeah, linearization or linear equations are quite good. particularly because we can, from a linear system, we can derive the transfer function, which is what we work with most of the time. So if you see anything looking like this in your differential equations, you're probably working with a nonlinear system, and you've got to do a little bit of work to get it in a form that you can use directly. And yeah, that's the idea of linearization, is just taking derivatives around a certain point, getting the slope of your plant function around that point, and evaluating it. Laplace transforms. Has anyone not done Laplace transforms before, or worked in the frequency domain or the S domain? Feel free to speak up if you have not. Otherwise, yeah, great. Sounds like we have all done Laplace transforms. Yep, a while ago, no worries. So we're not going to go too deeply into Laplace transforms, but basically the idea is we can analyze differential equations in something called the S domain, or the frequency domain, and that's a really powerful tool. The idea is, and we'll go through this, is that we can describe a linear differential equation in the S domain instead of the time domain. So the time domain differential equation looks something like this, and hopefully you're all comfortable with the dot notation for derivatives. So double dot is second derivative of y, single dot is first derivative of y, and y is just the value of y, and this is u. So this is the time domain version of a differential equation. We've got some linear combination of y's and its derivatives, and some linear combination of u's and its derivatives. So when we use Laplace transforms, we basically use these relations to move between the time domain on the left and the S domain, or the frequency domain, on the right. So y in the S domain is just y as a function of s. The derivative of y is s times the Laplace transform of y, and the second derivative of y is equal to s squared multiplied by the Laplace transform of y. So in the S domain, we go from working with derivatives to working with powers of s. So this is the equivalent differential equation in the frequency domain. So we've just substituted, wherever we see the second derivative of y, we substitute that with s squared multiplied by the Laplace transform of y, and so on, and that's how we can get those. And notice how in the time domain we usually use lowercase letters, and in the S domain we usually use uppercase letters. So hopefully that's a little bit enough of a brush up. Some other quick terminology is when we see S in the S by itself in the Laplace domain, we can sometimes refer to it as a differentiator. And when we see 1 divided by S, sometimes we'll refer to that as an integrator. So this is just some terminology. It'll make a little bit more sense later on, but it's got to do with how these map between the time domain and the frequency domain. So S is a differentiator, 1 on S is an integrator. So you'll see that terminology a fair bit. All right, grab your pen and paper. If you want to, you can probably do it in your head too. To derive the transfer function, we want to put the Laplace transfer, the S domain version of the differential equation in the form of output divided by input, or y divided by u, equals some function of s, and that's g of s. And we call that the transfer function. So here's an example of manipulating that differential equation in the S domain to the transfer function form. So output y divided by input u. And we get this, this rational polynomial of functions of s there, 0.5 divided by 2s squared minus 3s minus 5. So this is what we call g of s. And yeah, transfer functions are probably the easiest, most succinct and compact way of referring to what your plant is doing. So what your system that does the interesting things does. So we can just refer to it by the transfer function. That pretty much captures all the relevant behavior that we need to. So if you've followed so far, we look at the system dynamics, use equations of motion to derive a differential equation. We then take that differential equation into the S domain by applying the Laplace transform, and then we rearrange that differential equation into the transfer function form, which is output divided by input. And we refer to that as g of S, so g as a function of S. And when we say the plant, we can just give that this function here, g of S, and everyone knows what we're talking about. Right, so some examples. Hopefully you can get the chat going and jump on the mic if you feel comfortable. Let's have a talk about some of the key features of the following control systems. So let's think about, what are the state variables going to be? Are there equilibrium points, and if so, what do we think they are? Are the systems linear or non-linear? And what do we think the plant transfer function is? Although I think I do just give it away at the, on the slide. So let's see, what's our first one? So a mass on a spring. A half kilo mass on a spring with a spring constant 4 newtons per meter is acted on by some force U of t. So that could be a problem that someone's given us, and we need to discuss those points that I said. So what did I say first? What are the state variables? Anyone want to have a try at thinking what those state variables are for this system? Yeah, y and u are what we refer to generally. Yeah. What do they actually mean in real life? So we want to think about what it means in real life. Yeah, exactly. So is it just displacement for the state variable? We may be interested in its derivatives as well, right? Yeah. Yeah. Exactly. So the acceleration, the velocity of how that mass is moving around. And obviously our input is a little bit cheap here. I've given it as U of t, so input is just the force that we're putting on it. So always try and link these things back to what's happening in real life, I find. Don't get too wrapped in just thinking about them as y and u. And here's how we would define the transfer function. Here's our equations of motion, F equals ma, and then here's our force, our acceleration, so 4, this is our spring constant term, and this is our driving force. And then we can just apply the Laplace transform, rearrange that, and get our plant transfer function in the form of output over input. What else did I ask? So are there equilibrium points for this system? Yep, exactly. So we can, well, just be careful because there's a driving force in this one. So we set derivatives to 0, so that would get rid of this term. So we have 0 equals minus 4y plus u. So our equilibrium is actually a combination of the position and the driving force. Yeah, so you can imagine if I put a constant force in, it's going to put that spring and the mass somewhere else, but if I hold it constant, it's still going to be an equilibrium point. If the driving force was 0, then yes, the equilibrium point can be shown to be 0, the center point of the spring, whatever that proper term is. Good. So yeah, don't forget it's only the derivatives that we set to 0, everything else we can keep. Can anyone see a shortcut of getting the equilibrium points from the transfer function? What if we only had g of s? think about what happens when we set this term to 0. How does this term, what changes, what does this term contribute to the Laplace transform and the transfer function? The s squared, right? So if the derivatives are 0, that means we can set any s's that we see in the transfer function to 0, and we should recover the same thing. So this would say that an equilibrium point would be 2 divided by 8, or 1 on 4. And you would be able to see that from this as well. So that can be a little bit of shortcut. There's a little bit of finesse around that, but yeah, often steady state behavior. If you set s's to 0, you can typically recover some information about steady state behavior from the transfer function. Good. What else did I say? Linear system? I think so. Yeah. So we didn't see any mixing of variables and no odd sine or cosine terms or things like that. Great. RLC circuit. There's the differential equation. I won't make you do phone again. So state variables, y and u. Obviously, I've used the canonical convention for y and u, input and output. But what are they in real life? Well, it depends on the circuit, but the voltage that we're inputting to the circuit and the voltage that we're outputting or measuring. I think this is a parallel RLC circuit, so be the voltage across everything. The equilibrium points. What's an equilibrium point for this one? Yeah, exactly. V in equals V out, which makes sense for a parallel RLC circuit, right? If you've got an input here and you've got it's parallel across everything, when that output is just basically all the nodes are connected and you're just measuring that input. So the output equals the input at equilibrium. Good. Stable or unstable? A little bit hard to think about, but this is a stable equilibrium. And then obviously I've derived the transfer function here. Just be aware with transfer functions, we usually like to have the leading term of the highest order s in the denominator as 1. So we just factor things out so it looks like this, and that's generally a standard form for transfer functions. That's why you've got these sort of weird looking fractions that may not make sense at first glance, but it's because we want this leading term coefficient to be 1. Excellent. And this one's obviously a linear equation as well. What about a pendulum? Pendulum with mass m and length L is acted on by a force F. So what are the state variables for this guy? Yep. Exactly. Yep. So our angle, and so the angle that the pendulum makes with the some sort of origin or coordinate system, and then the force that we're dealing with then. So I've used theta directly here instead of u, and f of t instead of y. Is this a linear or nonlinear system? Nonlinear, yeah, we've got cosine terms here, and also a some sort of multiplication here between the state variables, so the input force and the angle there. So this to analyze this one properly in terms of a transfer function, we would need to linearize this system. Does it have equilibrium points? Think about this both in terms of the differential equation, but also think it back to the physical system as well. Yeah, where are they?
Physically,
Yeah, physically.
it'd be at, physically if you're at the point of whatever force you acted upon it, and then there's no acceleration.
Yeah, so if
But angular acceleration.
exactly, so if I'm inputting a force to my pendulum, imagine my pen is a pendulum. If I'm inputting a force, there may be an equilibrium point that holds it up here. If there's no force, there's obviously an equilibrium point at the bottom. Any others? Inverted pendulum, excellent. So if my pendulum, instead, if my pivot's down the bottom and my pendulum goes up the top, I've got an inverted pendulum, and there is an equilibrium point where the pendulum just points straight up. So can we see that on here? So this term would go to 0, and then we have 0 equals f by cos of theta plus mg sine of theta. So you should see that there's some sort of relationship where a theta equals, if you set, well, let's say there's no force acting on it, so the cosine term goes away, and we just have mg sine theta equals 0 to sort of calculate those equilibrium points. And where does mg sine theta equal 0? Well, it equals at theta equals 0, which might be down the bottom, but also at theta equals pi, which is up the top. So there's another equilibrium point there. Which is a stable and which is an unstable equilibrium? Yeah, exactly. So any small perturbation of my regular pendulum is going to take that back to the equilibrium point. For the inverted pendulum, that's not true. Any disturbance is going to take it away from the equilibrium point. So that is an inverted, unstable system. Right. How are we doing for time? 5:40. Yeah, I think we're on track. So all that work to establish this idea of a plant. We haven't actually talked about any sort of control yet, so we're going to get into the control part of it now. But we had to put in this bit of a work to talk about the plant and the system before we can start talking about control. So this should hopefully make plenty of sense now. Something that I couldn't quite, well, it didn't confuse me, but it didn't really make so much sense to me, control systems and how they were useful in a way, particularly like the idea of an electric motor, right? We're just used to applying a voltage to the motor, and then the motor does its thing and turns, and maybe we might need to apply more voltage to get more speed or something like that. Control is sort of like that, but it takes some of the guesswork out of it in a lot of ways. And control is all about choosing an appropriate plant input U based on the current state of the system to get the plant output to do what we want. So that desired output might be to hold a steady state, or maybe like track some sort of signal and follow a signal. The signal that we want the plant to get to is called the reference R. And I guess when we're implementing the controller, as users, we no longer think about applying the input U to the plant. That's the job of the controller. What we do as users, we specify the reference value R, and then let the controller choose an appropriate control input to get the system to do what we want. And the controller is going to do the best sort of job, and there's different controllers that we can implement that do some things better than others to basically get that plant to follow the reference as best as we can. So we're no longer just applying like a voltage to a motor. What we're doing is saying, I want the motor to turn at 500 RPM. And then the controller says, what voltage do I need to apply to get that motor to turn at 500 RPM effectively? And if I change it down to 50 RPM, how do I move from the fast speed to the slow speed? That's what the controller does. Now the controller itself can be characterized by a transfer function. And we call this transfer function C of S. And when we talk about designing a controller, what we're doing is designing the transfer function C of S, and then taking that transfer function and implementing it in software or hardware. There's two main categories of controller, open loop controllers and closed loop controllers. Open loop control, this is a type of control where the controller does not have any knowledge of the current state of the system. So we just choose a reference, the controller is designed, and it just is going to come up with an output, an input U to the plant, and then the plant takes that input, does its thing, and gets to its output Y. And the controller doesn't have any idea if the plant is actually doing what it's supposed to. So open loop control is around, but it's not very sophisticated. It can be somewhat effective. For more robust control, we want to implement what's called closed loop control, which is this one. In closed loop control, the controller does actually have knowledge of the current state of the system. So a reference R is compared to the current plant output Y. So we need to know what the current plant output is. It generates what's called an error signal. We refer to that as E. And then the error signal is the thing that's input to the controller. And the controller then chooses an appropriate control signal to input to the plant. The plant does its thing and then outputs the value of Y. But we've got some sort of feedback loop here. The feedback loop feeds that value back into this reference and generates the error term, which then goes into the controller, which then generates a U. So we can actually correct for any errors that the plant is doing with our, that may not be working correctly. Maybe someone's there and stuck a stick in the cogs or something like that. A closed loop controller will know that our gears aren't turning anymore and can, shut the whole thing down or crank up the power and break the stick. Open loop control would just say, yeah, I'm just going to keep on doing what I do best, is telling the plant to go to this value. So let's have a think about some real world examples of the two types of controllers. So some of them might be obvious, some of them less so obvious. I'd like to get your ideas of what you think might be some interesting controllers and types of control that you see. And particularly I want you to think physically about what sensors are being used in the feedback loop if it's a closed loop controller. And maybe have a think about what the pros and cons might be of the different types of control. So here's some jumping off points: a kettle, a toaster, cruise control, an electric drill, a stepper motor, servo motor. And then we want to have a think about whether they're open loop control, closed loop control, what type of sensors are used if they are closed loop. Yeah, it's a good question. I'm not super sure myself. I think for a kettle, what do? You hit the switch, voltage starts going through a heating element. I guess there's two options there for a kettle. It's either going to be on a timer, or there's going to be some sort of temperature probe in there, which I think is more likely what happens, because have you ever left the top open on a kettle and it just keeps on boiling away because it never quite reaches the temperature that it's supposed to? Yeah, I think actually, I think if there's a temperature probe in there, we've got closed loop control on the kettle. What about the toaster? Yep. Yeah, timer. So would that be open loop or closed loop? Open loop for that one, yeah. Exactly, open loop control. That's what I was thinking as well. Cruise control on a car. relatively sophisticated. I would hope cruise control is closed loop. Yeah. So what are the sensors involved in that feedback loop? What's happening? What's our control input for cruise control?
It's probably having a look at the wheel rotation speed to determine the car speed. There might be accelerometers within the car that they can determine stuff. I know that's something they use for ABS and was it stability control, especially if you're like cars.
Yeah.
It comes with a little engine dynamics as well. Like, at a particular speed, there would be a certain amount of fuel consumption. So the fuel consumption is also constant to have that particular power output.
Yeah, exactly. So there's a few things that go into implementing cruise control, but I think most importantly, the feedback being the wheel speed. I don't think they measure true ground speed. So for example, if the wheels were spinning, you'd get a false reading on your cruise control speed. If you wanted to design a super robust cruise control system, you might actually measure physical ground speed or speed on a GPS or something like that. So there is room for error in these sort of things. What about an electric drill, like a hand drill? I think this is quite an interesting one.
So with the hand drill, at what point does it stop, or does it need to? If something jams it or something?
Yeah, so there's like some hand drills have like a mechanical clutch in them. If you tried to drill and something binds up, it does. Yeah.
Should be more like an open loop system, right?
Yeah, so simple ones are open loop, right? Cheap drills are just open loop. You squeeze a thing, and then there's maybe some sort of voltage divider or voltage controller in the trigger system that then just applies a voltage to the motor. Fancy ones actually implement closed loop control. The trigger actually sets the motor speed, sets the reference, and then there's a feedback loop on the motor itself, which tells how fast that motor is spinning. So if you do get more load on it for a given trigger pull, that the controller tries to compensate and actually start turning faster if the load increases and it starts to slow down. So the feedback on electric drills typically is, have you guys ever heard of a Hall effect sensor? Yeah, so a Hall effect sensor senses a magnetic field. Basically, so if you imagine you've got a motor spinning, that's going to generate a magnetic field. And if you've got something that senses a magnetic field there, you can sort of know by the way that magnetic field changes and what the signal to that Hall effect sensor is, how fast the motor's turning. So yeah, sort of more complicated electric drills have feedback in the form of a Hall effect sensor, which then can tell you what the motor speed actually is. Stepper motors, if you've ever used them before, open loop. So there's a thing called, when you use a stepper motor, they can miss steps. If anyone's used that before and had a servo motor, a stepper motor skip steps, you can get it out of sync. There is closed loop stepper motors that do have some sort of feedback to the absolute position of the step, but typically we just work on +1 step, +1 step, +1 step, instead of go to this point directly. And servo motors is a good one. Those little hobby servo motors, they all actually have a little controller in them. They're closed loop, which is quite handy. If you try and change the angle forcefully on a servo motor, it will try and correct for that and come back to the angle that you've set it to. Anyone have any other ideas of control systems that they've seen? Open loop, closed loop. Thermostats is a classic one. Yep. Closed loop or open loop? Yeah, so there'll be some sort of temperature sensor there. I also like the idea of humans as a control loop, right? So we are very good feedback systems for a closed loop controller. Even for a heater, if you've got a heater that just turns on and off right? So that it's just open loop. It just, once you turn it on, it just runs. A human acts as a feedback loop in that. If it gets too hot, you go, oh boy, I better turn this heater off. So you walk over to it and turn it off, and then it starts getting cold again. And you go, oh, I'm a bit chilly now. I'll go walk over to the heater and turn it back on. So the idea of the feedback loop is quite powerful, and often actually developing feedback loops. I remember reading somewhere there was a lot of investigation into designing controllers, I think, that would mimic a human and the way that a human would control a sailboat in high seas, right? So the human is like the ultimate feedback loop in that. So many different variables happening, so much different points of control for that. But humans can do a lot in taking in the current situation, the current heading of the boat, how much wind there is, and choosing the correct control inputs to the steering wheel, whatever it is on a boat. It's not a steering wheel. And then, the sail trim and things like that. So some really powerful stuff there that humans can do. But we can't be there for everything.
There's actually a really interesting theory called McClure's crossover theory that talks about how you can sort of model human behavior. It's part of Exchange University I looked at.
Yeah, nice.
Looking at that based off how humans behave with autonomous cars. Based roughly off memory, it's like the general open loop model of a person is probably around first order. So we're very good at tracking and stuff. But when it comes it's interesting how human adapts to the behavior based off the model. So if, for example, the human brain can kind of like do derivative control once it's had enough exposure to kind of like create our model. There's no like clear way to describe what the human model is, but it's like a basic model has been applied early on. Yeah, it's called McClure crossover model.
Yeah, nice one. Post up a link if you can. I'd be interested to have a read.
There's like a open courseware slides, but I don't know about the actual lecture itself.
Sweet as, thank you. All right, let's keep motoring on through. I think we're almost, we're sort of there. What's going to be the balance of this? Yeah, let's go for a little bit more, and then we'll have a break, and then we'll come back and we'll do the practical example. So, designing controllers. I'm going to talk about 3 different types of controllers, and they're going to be closed loop controllers. And they're all sort of interlinked, and these are really sort of these are the main ones that are being sort of implemented in industry, I guess. I think I'm just in answer to that question. I'm not going to talk about specific things. What I hope to achieve with particularly the practical component is going to be how you can take these ideas of the theory behind it and then apply them to your projects or to physical examples, because particularly feedback control is quite good because the format of it is we only deal with an error signal as the sort of the thing that we're interested in. Right, so your error can be from anything. It can be difference of temperatures, it can be difference of position, it can be differences of speed or something like that. If all we're dealing with is the error, that opens up a whole wide world, because as long as we can implement that feedback loop, we can implement one of these canonical controllers and we can have a decent control system and decent control over what the plant is doing. So I hope that I don't talk specifically about these sorts of things, but particularly not around like large scale control sort of stuff. The aim for this will be, if you had a project, a small robotics project or a small electronics project, you could take the ideas of this away and implement those in those sorts of projects. So, a proportional controller. or a proportional feedback controller, proportional gain controller. If we set the controller transfer function to just some positive constant kp, we get what's called this proportional feedback controller. The way that I like to think about this is if you think about what the error, how the error goes to the control signal, is the control signal is proportional to the error. The more error there is, the harder that controller is going to correct for what that error is. And this will come in, I'll make this super clear when we do the practical component. They're quite simple to implement, and they can be quite effective, but sometimes there's extra requirements that cannot be realized with just the proportional feedback controller. So just for a quick example setup, there's a motor that's described by this transfer function. And if we want to implement a proportional feedback controller to hit 500 RPM, so this would be the angular acceleration in radians per second, 52.3, corresponding to 500 RPM. Our control loop is going to look like this, right? So our reference is here, so it's a square wave. I've just got it turning on to 52.3 radians per second, dropping to 0, turning on to 52.3, dropping to 0. Here's our error term that comes out here. So here's our Y output over here. It gets fed back in and taken away from the reference. So whatever the difference is, that's our error term. Here's the controller part of it. So here's just a gain. So that whole C of S block, when we were talking about this general closed loop control setup, C of S has just become some gain K, some constant K. And here's our plant model transfer function. And then if you're familiar with Simulink, this is just a plot to generate this. So if you want to generate it yourself, this is what it looks like. But here's what the output looks like. Hopefully you can see that. Okay. So yellow is the reference signal. So the pulse turns on to there's our 52.3 for a few seconds, turns off, turns back on for a few seconds, turns off. So that's our reference signal. This is what we want the plant to be doing, right? So we want our motor to turn to 52.3 radians per second, then turn off, turn on, turn off. Y is what our motor is actually doing. So that's the red one. So you can see the motor, when our reference turns on, our motor starts to spin up, the speed increases, and it hits this value of just above 40 not RPM, but I'll just say RPM, just above 40 RPM here. Turns off, takes a little while to spin down to get to 0, spins up, spins down. And U, the blue one, is the control input. So this is what we could think of as the voltage input to the motor here. So there's a bit of a spike at the start, and then we hit a nice level voltage, negative spike there, which may or may not be allowed actually, and then hit 0 and so on. So there's the 3 different signals. And that's with a gain of 0.5 there. This is this type of response that we get. So this behavior here may not be super ideal. Why is this happening? We've told our reference is like a bit over 50 and we're only hitting a little bit over 40. That's not ideal. What happens if we change the gain of our feedback controller? Here's what it looks like with, oops, that didn't change. Why is that? Oh, I know, my zoom is not right. That's better. So here's what it looks like with K equals 5. So again, our reference is the same. We still want it to go to just over 50, drop to 0. Our output Y, the red, is now coming much, much closer to that reference value. And it's getting there much quicker now and dropping much quicker. So this is generally better. But what's the downside of that higher gain now? Can anyone see it? Yeah, exactly. Probably physical limits of the motor, what the voltage can supply, right? Or even what the motor can take. We don't want to burn it out. There might be like a peak in current here that exceeds our requirements. So increasing the gain is good, but sometimes we need to be careful of the the trade-offs with that. So simple.
Was a second order system, it might oscillate as well.
Yep, exactly. There's my Zoom playing up again. Okay, so instead of a straight up proportional gain controller, we can include a different term, and this is the form of our controller now. C of S equals Kp plus Ki divided by S. So if you remember from before, we would refer to this as some sort of integrator. 1 on S is an integrator. So this is why we call it proportional integral controller, or PI controller. It's slightly more complex in the controller design, but it offers some more flexibility. And particularly the inclusion of this integral term in the PI controller helps us minimize steady state error. So back on this one, right? This is what we'd refer to as steady state error, the difference in the steady state of what's actually happening with our plant with the desired value. So there's a steady state error there of about 10 units, or a bit over 10 units there. Inclusion of this integral term, we'll see, can help to minimize that effect. Conceptually, I want you to think about it like this, right? The error term gets accumulated by the integrator. As the controller corrects for the current error, it also corrects for any previous error that still exists. So over time, that integrator adds up error that exists and sort of keeps a hold of it and says, if that error is still there, if it's still there compared to last time, I'm going to say, bump up my effort a little bit more. And if it's still there, keep bumping it up, because you're getting further away from, you're still not getting any closer to that reference signal. So that's the idea of the integral term. It accumulates the error and helps the controller to correct for steady state error. So we implement that again on our motor example. We're going to take these values, and we'll see that the controller can make that motor reach and follow the desired RPM quite effectively, a lot better than the P controller alone. So here's how we implement it in Simulink in a block diagram. Here's our transfer function. Our plant hasn't changed. Our feedback loop hasn't changed. All we're doing is changing the controller. And here's what it looks like. So again, we see that now our motor speed is ramping up to our reference, and we're getting quite good tracking eventually of this of that reference signal. We're sort of spot on with it. Same thing when we drop down to 0. There's still a little bit of time for it to reach that value, the rise time that's called, how long it takes, but we get there and we do a pretty good job of tracking it. So the last one is this idea of PID, or proportional integral derivative controller, and our controller has this form here, Kp plus Ki on S plus Kd on S. So remembering back, S we refer to as a derivative, or differentiator, so that's why it's called this. It's again more complex, and they can offer quite excellent control over the system response. And the derivative term allows the controller to now correct based on the rate of change of that error. So if the error is changing really quickly, our controller can then sort of take that into account. And if the errors starts increasing really quickly in one direction, the controller can say, quick, you better start turning really hard in the other direction to compensate for that. So that's what the inclusion of the derivative term includes. So we'll show the example. I just want to talk about the idea of noise on that on the signal. If there's noise in the error signal, which could come from noise in the feedback loop, imagine that means any noise means that it's changing all the time. So a derivative term is going to pick up on those changes, because that's what it does, derivative, rate of change. It's going to pick up on that change, and it's going to try and correct for that. It can't, it can't distinguish whether it's the reference signal that you want it to follow like that, or just noise. So derivative terms you need to be quite careful with when you include them, because they can have some quite undesired effects, particularly with high frequency noise. And after a bit of reading, I found that the derivative term in industrial control is not really used so much. Typically, you'll just see PI controllers. And it's mostly because of this. They take a little bit of careful getting used to, and often your PI controller will get you the type of response that you need. So here's a... Yep. Mm-hmm.
Why is it the form that it is? It's a S squared over S kind of form.
So this term here just comes from putting this in a fractional form.
Together, right.
Yeah. So if you multiply through by S on S to normalize that fraction, it'll come out to be this. So this is the term that we typically like to visualize, but oftentimes you can analyze a transfer function much easier if it's in a rational polynomial form like this. So there's sort of two sides. This one's easy because we can see exactly what each term is doing. This is the proportional term, this is the integral term, and this is a derivative term. In this form, it's not so clear. So it's actually a little bit harder to implement this in Simulink because it starts complaining about improper transfer functions. This is improper transfer function, so the order on the top is higher than the order on the denominator. So this is the way to implement that. You implement the derivative term separately using this derivative block like this, and you just add them together. So the P and I terms are wrapped up in this transfer function, and the D term is captured in this one. And you can see I'm using a PD. Sorry, that should be KD there, not PD. I'm using KD equals 0.13. And that's the gain block there. Yep.
What's the problem with transfer functions again? Is it something to do with causality?
They are unstable and non-causal basically, or they're typically unstable. So if you think about what happens at high frequencies with this one, is sort of the easiest to see. So high frequencies are for very large S. So if we let S tend to infinity, the numerator blows up, and our controller transfer function blows up as well. So for proper transfer functions, with the order on the bottom is higher, you see the opposite effect. As S gets really high, the transfer function will drop to 0. Yeah. So that's the idea with that. It's honestly, it's quite a subtle discussion, I think, about proper and improper. It's not something I really grasped fully, I think, from my time in control systems course. The idea of that, yeah, it's quite subtle. But anyway, here's how we'd implement that in Simulink, and we get this sort of weird looking response here, using those terms with our good old motor example. And it's complicated to analyze. I didn't spend too much time playing with the values for this one. We could probably get that to behave a little bit nicely. But the thing to notice here is we get this thing called overshoot, where the value of our plant output exceeds the reference value, and then we'll drop down to it, which is probably, may or may not be useful for us. Obviously, we might get a little bit quicker reaching that value, but yeah, we get this overshoot here. And yeah, the motor control signal is maybe a little bit less than ideal as well. How do we typically choose the constants? We'll talk about that in the practical example that I've got. We're going to do what's called the manual tuning method and play around with that, but there's other methods of tuning a PID controller. Ziegler-Nichols, as David mentioned. There's a few others as well, but they typically, we'll discuss those. We'll talk about the manual tuning and just really get a feel for what these constants are doing. What was I going to say? There's a lot of other different types of controllers. You'll often hear things like lead lag controllers come up. which sort of have to do with PID controllers. It's getting more into the theory side of things when you start talking about lead lag compensators and things like that. Phase margins and gain margins, they're all important, but not so much for the hobbyist, I think. But yeah, you'll come across that in control systems. And let's talk quickly about implementing the controller, then we'll have a break, and then we'll get into the hardware. Let's take a PID controller, transfer function of this. Using the knowledge of the transfer of Laplace transforms, we can get the time domain value of the plant input signal here, our control input, based on the error term. So this is rearranging the transfer function U on E to this, and then doing the inverse Laplace transform. We get something like this. So here's our integral term, here's our derivative term. And this is tempting just to try and implement. It looks quite readily implementable. We can do an integral, we can do a derivative. Particularly if we're doing anything on a microcontroller though, you'll need to discretize that particular relation here. And without boring you with the details, mostly because I didn't have time to derive the details fully myself, we use these discrete relations, and we arrive at this following relationship here, which looks a little bit scary. There's a lot of terms there, much more so than a simple derivative and integral, but that's all that's coming through. If we're implementing it with a time step of delta t, that's this, so the difference between successive updates of our system, tk being the current time, the control signal at our current time equals, this should actually be tk minus 1 there, that's my bad. And then we've got some other terms here which have to do with kp. We can see a ti here, which has to do with ki and kp, and a td here, which has to do with kd and kp. And yeah, this was just basically, I found the reference for this because the derivative is a little bit technical, but it involves taking these relationships here and doing a little bit of maths. And this is the algorithm that we want to implement for a discretized PID controller. Things we'll talk about when we get into the hardware is integral windup and actuator limitations. And we'll talk about those and see how they look. Okay, that's the end of the first half. We're going to take maybe a 5 to 10 minute break. I've got to get a little bit of stuff set up, and I'll come back and we'll jump into some practical control. You'll be able to see the effects of stuff happening in the real world if everything goes to plan. I only finished making this little contraption yesterday / today, so there's a high chance something won't quite work the way that I want it to, but we'll see. All right, yeah, we'll be back in 5-ish to 10 minutes. Thanks for joining so far. Hope to see those of you that are sticking around back then. Feel free to ask any questions if you need to, but yeah, I'll be back in 10 as I set up. Okay, sorry, it took a little longer than expected to get set up, but I think I'm good now. I'll just kick off the recording and I'll show you guys what we're dealing with. Perfect. All right, I've got everyone here. They're all back from various breaks, hopefully. Wonderful. Okay, so I'm going to try a little bit of sneakiness in that. Hopefully, if you can see my share screen, you can also see my camera. How's that going? Okay? Wonderful. Okay, so here's the system that I've got set up. I spent all day crafting cardboard and hot glue. So we feature a motor under here. It's a gearhead motor, just a DC motor. There's some connection at the bottom there. So basically a DC motor. It's hot glued to hell to this bit of cardboard, which sticks out here. The cardboard, you'll see why I've got the cardboard like this in a second, but essentially it's a some sort of inertial load on the motor. I've got the motor attached to my Arduino with a motor shield on the top to drive that particular motor. That's the cables going off this way. I've got the motor driven by a 12-volt source. The Arduino sits underneath. And the Arduino will go by the blue cable back to the computer to upload code to it. And also, I've got one of these ultrasonic distance sensors here, which is connected to the Arduino as well. So this sensor here can measure how far away something is from the sensor by virtue of sending a pulse, like an echolocation click, gets sent out, it reflects off something, comes back in, and basically we measure the time delay and get the distance based on the time delay between the echolocation pulses. So the idea is I'm going to use this distance sensor to implement the feedback loop. So my output from the plant is going to be some sort of distance, and the feedback is going to be, that distance signal. I'm going to bounce the distance. I'm going to bounce the distance reading off of this funny-looking, wobbly reflector thing. It's just got a few kinks in it so that it's not just a purely flat surface to reflect off. It's got a bit of some features on it. So the sound should hopefully bounce back from whatever angle it hits at. And obviously then this is my, the distance between the sensor and this thing is the output. So this is Y, that distance. And the input is going to be the control signal to the motor. So the motor obviously turns this left and right, or clockwise, counterclockwise, right? So by virtue of the motor turning, the distance between the sensor and the paddle, I'll call it a paddle, is going to change. So maybe not a completely useful physical system, but it's going to implement the idea of a feedback loop, a control signal, and we can see how the motor is going to act in response to the reference signal and deviations from the reference signal. And we'll talk about some practical things that have to do with that. Any questions so far? It's a bit of a cardboard wonder, but fingers crossed, it's going to work for us. I have tested it a little bit, but yeah, it's not fully tested, I guess. Yeah, exactly. Cardboard and hot glue. There's no blue tack on it though, surprisingly, or rubber bands. So yeah, it probably will fail then. All right, let me put that down for a second and I will show you the code. So I'll just fire up my Arduino IDE and we'll quickly run through the code. Okay, so here's Arduino code. Quickly running through, a lot of it's just boilerplate setup, defining pins and whatnot. We've got control over the time step, so the dt, or the delta t in the in this relationship. This one here, so dt, we've got control over that. We'll talk about the saturation value for the control signal, but essentially we want to make sure that I don't spin the motor too fast or too quickly, because otherwise, you imagine it's a reasonably powerful motor. I don't want this thing spinning out of control. I want to be able to turn it off quickly if I have to. So I implement a saturation, so it's going to be limited to 120. I think the maximum's 256. In fact, I might even drop that down. I was playing with it before. Might drop that down to about 80. We've got our Kp, Ki, and Kd values here that we work with. I'm going to set these back to zeros. I'm going to set Kp to be 1 just as a starting point. I've got my reference signal R, so the distance that I want my controller to maintain between the sensor and the paddle. So I've got that set to be about 34 centimeters, and we can adjust the distance. Obviously, I might have to tweak that. And then some declaration of state variables. If you saw, we needed the current error, the previous error, and the previous error. So from 2 time steps ago, we need the control signal, and we need the past control signal, and we obviously need the output. Some other setup, some other boilerplate stuff, so setting up. I've just got a quick check here for implementing Ki and Kd equal to be 0, because if you have a look at this, these terms here, the Ti and the Td, when Ki is 0, obviously things break. So I just need to take care of those in the code. And then our main control loop looks like this. So we check whether our time step has elapsed, and if we have, we go into the main control loop. Otherwise, we just do nothing and wait until the time step has passed. Updating the time, I get the distance from the sensor. So I calculate an average of 50 different readings from the sensor, because these sensors can be quite noisy in the values that they return. So most of the time they're going to return something reasonable, but sometimes some noise will get in, a spurious reflection from somewhere. So I get some averages there. Here's our error term. Obviously, here's our R minus Y. Here's the control signal. Again, the if and the else is just to make sure that I handle the fact when that divide by 0 term comes in. So I've just got that handled. Here's the full algorithm from this one. So that's the full algorithm implemented, and the reduced one underneath is what it reduces to if Ki and Kd would be 0. So that can be useful too. So I don't need to keep changing which one it actually uses. Here's where I implement the saturation. So if you imagine this controller, here's the actual controller here, the code, just like 2 lines of code, right? I just need to check my saturation. So the controller may say spin your motor up to 5,000 RPM. I don't want that. I want it to be limited. So this is where I bound that. It's just a simple make sure it doesn't go above and below those values of the saturation that we defined above. Here's where I send that control signal to the actual motor. So basically telling it to run in forward and reverse and then setting the speed. That's just the way you interact with this motor. And then we're updating the state variables for the next loop. So setting the error, setting the previous error, setting the previous control signal. And then we're going to write some outputs and then go back to the start of our loop. And here's the functions for reading the distance from the sensor. Any questions there? Cool. Okay, so what I'm going to do, I'm just going to comment out the two lines where I actually send the control signal. Okay, because first we're just going to have a look at the outputs in the serial plotter, in Arduino's serial plotter, and just see what happens when these things start to move and the proportional stuff and how the stuff affects it. So give us a second. I'm just going to set up the camera in overhead form, and then yeah, we'll get stuck in. Okay, hopefully you'll be able to see that happening. Apologies for the slightly messy floor and the somewhat odd setup. Thanks for all dealing with it. It's remote COVID learning for us, I guess. Okie dokie, so I think I should be good enough to go. I'll just plug in my Arduino and quickly upload this code because it's starting to move around, which I don't quite want just yet. Great. And I'll bring up the serial plotter, which is a super useful tool. If you haven't used it for monitoring your variables for Arduino, it can be quite handy. All right, shrink that a little bit. And there, okay. Hopefully we can all see. So the blue line is Y, so the value of the sensor reading. So you can see there it's sitting around 30 centimeters or something. So the distance between the sensor and the paddle. The red is the error term. So that's sitting on this one here, so slightly above 0 at the moment. And the green is the control signal U. So this is what's getting sent to the motor. So a control signal of 80 units. Let's just call them units in this case. It's technically a pulse width modulated signal that's managed by the software setup. But let's have a look at what happens when we change this. So let me just set up. I want this to roughly be my equilibrium, I think. So I'm just going to alter my equilibrium, and we can see that the value of Y, that's coming to be about maybe 30. So I'm just going to go up and change my equilibrium slightly lower, maybe 31. And upload that, and we should hopefully see these variables change. So my error is a little bit less. So reference is just with my my paddle sort of set up vertically, horizontally. Okay, here we go. That's a bit closer. We can change this. So Kp is 1, Ki is 0, Kd is 0. That means that our control signal is just a proportional term of the error. Okay, so remember, error is red and green is the control signal here. So let's see what happens when I change the paddle so I get some error coming through. Okay, so my error there is a negative value, and we can see that my control signal has traversed downwards to hit my negative saturation point. Okay, and even what I might do, I might just get rid of this saturation for a second to see what happens if we don't have that saturation in there. Okay, so without saturation, look at what happens. So remember, green is my control signal. So this is my controller telling my motor to go minus 300, minus 400. It just keeps on going and going and going. I can get it to come back in the other direction by getting my error to go positive. So in the other direction. So error is now positive. And you can see my control signal is now shooting back up. And it's gone way positive. And it's just going to keep going positive and positive and positive. So think about what Kp is doing. Okay, so if error is 0, so I try and get my error to be 0, my control signal shouldn't change at all, right? Because if we have a look at our code, control signal equals previous control signal plus Kp times the error. So why am I adding uprev for the proportional controller? So that has got to do with the discrete implementation of a controller. So it's got to do from going from the continuous time solution of a PID controller to the discrete time implementation of a PID controller. And that's just the way it happens. You can derive it, but this is the formula that comes out. This should technically say T of K minus 1, so this is the previous term here. So when you do find out that value, you get a K minus 1 in there. So that's the previous. So yeah, based on the error, I can get the control signal to traverse. So Kp is sort of like the slope of this line, right? For a given error, my control signal is going to start trending and changing. So that's with Kp equals 1. If I change my Kp to be something like 10, so I increase that proportional, what do we think is going to happen to the slope of this line? Yeah, it's changing much quicker now. The error is the same, but because I've upped that Kp term, it's now changing much quicker in relation to that error. So if I bring my error, yeah, go ahead.
So the reason why it's still growing for like when you're keeping away from the equilibrium point is because of the integral control, is that correct?
Not the,
Tracking the difference, no?
no, it's not the integral control just yet. So we're still just on proportional feedback. So we've got Ki and Kd set to 0. This is something referred to as integral windup. And that's got to do purely with the discrete realization of this controller, okay, and the way that it's implemented. The naive, yeah.
Tracking the previous state, so it keeps growing based on the fact that it's still an error.
Yeah, there is. It's sort of like that. It's a little bit hard to explain. The derivation of this this discrete form is you get this sort of continued additive error come in there just as virtue of doing it that way. So it's not to do with the integral term in the controller. It's just purely because we've discretized it. So it's called integral windup or integrator windup if you're looking to sort of do a little bit more reading into it. But you can see here, without putting some sort of saturation term in there, or making sure we bound our control input, we can run into some issues, right? Because you imagine, right, if we're trying to get our control system to do something and it's really, really high, you know, we may be shooting off down here, and even though our error is only small, we still could be telling our motor to spin really fast in one direction. So that's the idea of this this bounding of the control signal and the saturation. So I had those set to 80, so positive and negative 80. Let's see what happens when I implement those. I'll just close that off to clear it. Okay, so our green here is now bounded by negative 80 down here and positive 80 up here. And with the KP that I've got, you can see it's bouncing between those pretty quick. So for even a small positive error will get the motor going to those saturation values very quickly. Right. Any questions about KP so far? What I'm going to do is I'm going to turn the motor on now. The motor hasn't been doing anything, it's just been me. I've stopped the control signal. Let's turn our motor on and see what happens, hey? Fingers crossed things don't blow up. Things are sort of blowing up. Okay, so you can see the motor is, what's kind of a better way, sorry, let me just stop that for a second. I need, yeah, it might be too high still. Oh no, I put it back to 1. Yeah, let's go quite small just to ease us into it. I've got to obviously plug it in. Okay. So with a quite small proportional gain, you can sort of see it. I might just close that off so it becomes a little clearer. So with a quite small proportional gain, I don't know, you guys probably can't hear that, but the motor is whining away. It's getting a little bit more. It's starting to go now. There we go. We're getting control back the other way, swings it back. It's still not quite an ideal situation. We're getting this oscillating sort of idea happening, which is quite typical of a proportional gain style controller, is this idea of oscillation, right? You'll see it oscillate around that equilibrium. We can change this up a bit. So if we increase the proportional gain, that means the error is going to start coming into effect quicker. So we should hopefully see, even though it's going to move faster, right, so we got those oscillations. Let's put that KP up again. 20. So it's going to kick in based on that error term more quickly. It's going to reach. That's a little bit more like what we want. Not really. It is saturating quicker. So my serial plotter stopped there. Let's see what happens when we bump that up again. So still oscillating. You may not be able to tell, but it's a little bit, you know, it's catching itself quicker now. It's not hitting the stops that I've got on there. It's not smashing too much into the sensor. It is a little bit. Let's try going up again. Oh, 500 will be too much. Let's go 50. Yeah, I'll see if I can get this plot coming back up. The plotter has been sort of playing up a little bit for me. Yeah, the plotter's not doing so great. We can go up again. Okay. So oscillations are pretty typical of a proportional or even just a PID control system. And they're actually, you know, I'll be honest, I haven't had too much luck tuning this thing the way that I exactly want it to. It's just, you know, it's a cardboard system. It's not so great. But the idea of getting those oscillations happening and then looking at the frequency of oscillations comes into play in some of those tuning methods like Ziegler-Nichols. You look at the frequency of those oscillations and you then base the Kp and the Ki and the Kd terms on the frequency of these oscillations and the value of K that got it to oscillate. So let's work with that with Kp. Let's introduce an integral term and just start bringing this one up slightly and see what starts to happen. So let's just start small. I can't recall what sort of numbers I was getting for this. Let's go 0.1. And just start to see what happens when we bring in the integral control. So already it's changed the way that the control signal changes. We got quite a high error, but the control signal is, I don't know if you can see that, but the control signal is only just, like, it's going up quite slowly. So it's going to be a while before that term reaches, because we've now brought in some, oh, that's gone a bit crazy. We've brought in the weighting of the previous error as well. So the way that interacts with each other changes the way that this controller works. So it's going to bring up this Ki term a little bit. See if we can get it.
The Kp might be too high.
Probably will be. Let's bring that down. Why am I getting some noise there? Let's bring that down to maybe 40 and see. I'll just bring up this Ki term. So yeah, control signal is starting to grow here. Might get a little bit more Ki happening so we can start seeing something to happen. So integral term is growing that error. Something's happening. Come on, motor, move.
Could you feel if the motor has like a little bit of a delay before it actually like?
Yeah. You can hear the motor whining, which has to do with the quantization. I think there's 8 bits of pulse width modulation. And as it steps through those lower level bits, you can hear the step changes. So
Maybe the inertia of just the weight of the cardboard is not really the motor doesn't account for that.
yeah.
Drag it enough, like the force being applied is probably
Yeah, so it's doing something not quite what I was. So this has changed a little bit from what it was doing before. It's still trying its best though. So this control signal is growing. It's growing in the wrong direction. Why is that? I think maybe my sensor was rebounding off a weird spot. Let's try bringing up that integral term again. Forget what I was dealing with. Let's go something bigger. See if we can get something happening. As you can see, I'm no tuning expert by any means. Oops.
I would poke the cardboard, what happened? Oh nice.
Yeah.
It's like this.
So you can see it seems like, yeah, it seems like the equilibrium is there. I think if I move this closer, should probably, yeah. So if I just displace that, it should start to come back towards that equilibrium. It's very slow response, isn't it? Well, that's not bad.
For the sake of stabilization. Oh, that's not bad. Yeah. There you go. Oh.
So it takes a while to recover,
Yeah.
but you can, yeah, you can see there's not too much overshoot. So it goes from the error, from that position, it reaches its equilibrium quite nicely. And once we get there, like you can see the control, you know, the error is almost zero here. So there's not too much happening, but the disturbances, it recovers sort of nicely. Let's have a play around a bit. Let's bump up the KP. Why not? See if we can get something more fun happening. Let's even go up and let's change the motor saturation up a bit. Let's go up to 120, get a bit more speed happening. No worries, Brett. Thanks for coming along. Appreciate it. So, I mean, something like that, what I've got there is a reasonable control scheme in some ways. I mean, it's not overly dramatic. It does some reasonable things. We don't have too much overshoot. What happens if we go really high on the integral term? We might be able to get some instability come back in.
Feeling that he's more a matter of sensor and actuator constraints more than actual
Yes,
values themselves.
as do I.
Delay in the reading.
Yeah.
There seems to be a delay in the reading, and there seems to be a delay in like how the motor responds to whatever signal it's receiving.
Yeah.
By the time it's given the correct adjustment, the delay in the sensor and the reading means like it's too late.
I would tend to agree.
That's what I'm observing.
Yeah. I had a lot of trouble, like this is a geared motor, because the original motor was quicker, but it didn't have enough torque to change that. So, can see we've got some sort of oscillations here. And particularly this sensor is not ideal because it's an ultrasonic sensor and it's working off the echo. Any movement is going to come into play with spurious readings from the Doppler effect. So yeah, and it takes time for the bounces, and we're doing, what was it, like 100, we're doing 50 averages of individual readings. So yeah, it's not ideal. Let's bring in a little bit of, well, let's drop this down a little bit. Let's go maybe 300, and then we'll bring in some derivative term and see what happens. Come on, upload, you know you want to. Yeah, so that's doing something. So let's bring in some KD. Even just a little bit I think was okay, and we can start seeing what that does. So you're going to have more responsiveness of the control signal to changes, particularly in like something like this here. See much more jumping around of that control signal compared to what's going on in the integral term. It's trying to do something. We might reach that equilibrium at some point. You know, that's getting sort of close there. Let's give it some disturbance. Takes a while to come back, but it's not going too badly. Let's see if we can bump up that KD a little bit more. So that was quite nice, that action there. Sort of found its way to something, you know, it's quite close to that equilibrium now. Sort of bouncing around. What happens if we change KP up a bit? So yeah, it's finding its way.
Thought, John.
Yes.
It's just off the topic of how we're talking about using an actuator constraint of the motor. Maybe something that might make it look more responsive is to figure out the minimum force of the motor, of minimum voltage required to start moving.
Yep.
So we set that as 1, but we just do a multiple or whatever that minimum term is.
Yeah, that's a good idea. Yeah, so you'd say only kick in above.
Right now, what I think I'm seeing is, it's kind of like there is voltage coming in, but that voltage isn't high enough to see any movement.
Yeah.
So by the time it starts moving, it doesn't adjust in time. Whereas if you find the mid, because I think it's just because of the weight and the friction of the motor and the meaning that it doesn't move. Whereas if you find that minimum movement, you start seeing more dynamics.
Yep. Yeah, agreed. So you could probably do like.
Wouldn't know how to measure that, but not fun to do this.
Yeah, I mean, you could probably set up something like found it. You could probably do. Yeah, but we need the motor to stop at some point too. Yeah. Interesting. I mean, the control scheme that's here at the moment is actually reasonable. It's one of the most pleasing ones that I've got so far. I'm going to bump up this KD term and see what happens. I mean, it recovers within 1 or 2 oscillations and basically hits that equilibrium. I mean, this can be a little bit misleading. You might look at this and be like, what's happening. Typically you'll find there's something called a dead band, which is, you know, we get to that equilibrium basically, and we don't, you know, even though there's a little bit of noise, you know, the difference in value might be like 2 or 3 centimeters, but that may be good enough for us. So you say, if my error is below these bounds, we don't need to do anything. So I think that's called a dead band, which I haven't implemented here. But yeah, see, this is quite nice. So this is a, yeah, it just takes a while to shoot back in the other direction, doesn't it? Yeah, see, that recovered in basically one oscillation, an overshoot. And yeah, obviously you can move that closer. We get a different equilibrium with a different response. So yeah, that's the idea. It's quite valuable. I mean, I certainly learn a lot from doing this myself, and it's quite easy. The actual control part of it is like a line or two to implement the control, and then yes, you can just play around with it and get a feel for it. So certainly, if you're interested, I think the setting up a simple feedback loop is quite powerful, and you can implement some sort of control. I want to come up with a few when I start running these workshops in person. I want to have a few different examples of these sorts of control systems. So if you've got any ideas or are keen to build something, let me know, because my view for this workshop is sort of we have a few different stations set up with some different examples. So something like this, something like a temperature control one, where you've got a thermometer sensor and like a heating element through a heat sink or something that tries to maintain the temperature. And you can just see them all work in sort of real time. But yeah, I don't know, I think that's probably about it, unless anyone had any things they want to see or questions to ask. I hope everyone enjoyed it. This is 12 volt supply, and it's pulse width modulated, I think, with 255 being full ball, 100% duty. So 120 is, you know, a bit under 50% duty. I don't know. I've done my workshop, so I'm not afraid to break things now. Let's bump this up. Let's go 180. Yep. Probably not going to notice too much difference because the control is relatively... Yeah, let's try and get some quicker actuation. So I think we could probably do that by KP. Let's go 500. Thanks everyone if you're heading off. Appreciate you coming along. Make sure you're on the MUEC Discord if you're not already. Good luck with all your exams. Let's get crazy. Yeah, you can see that I think the D term is probably maybe the integral term. Let's take this one down, maybe. kill it. Let's go a PD controller. Let's see what that does. Probably something horrible. Whoa! Yep. So yeah. Nah. So yeah, I mean the motor's got some give to it. It's got some kick. I haven't quite got it. You know.
It's embedded a really nice fly swatter.
Yeah. Yeah. Anyway, I better shut that off. All right.
I have to head up as well. Thank you very much for the workshop.
No worries. Thanks, everyone. Yes. Yep.
So do you always pick the constants based on trial and error?
No. No, certainly not. Good way to get a feel for them. What you would probably do, right? So the typical way to design something would be spend more time on the planning side of what is the plant actually doing. So modeling the motor, modeling the moment of inertia of this arm, modeling how the distance responds to the angle changes, and then having a look at what your G of S plant transfer function actually looks like. You have that idea. Once you've got that, then you can actually properly design a controller that sits there and does exactly what you want. So that's the full thing. If you don't want to go all the way into modeling this whole system with differential equations and stuff, that's when the tuning methods such as Ziegler-Nichols, and there's a few others floating around as well, come into it. They're a little bit more involved. You can the Wikipedia article on PID control is actually quite good. It's quite in depth, so I'd recommend checking that out. But basically, the Ziegler-Nichols method, you find with the proportional gain control, you find that period of oscillation that it starts oscillating at, and then there's basically rules for setting those different constants based on that period of oscillation and what gain sort of created those oscillations. I did try that a couple of times with this one. Didn't really work for me though. So yeah, I was hoping to demonstrate Ziegler-Nichols tuning, but yeah, it just wasn't quite working the way that I was hoping to. So needs a little bit more thought, obviously, my system. But yeah, no worries. Catch you later.